morning, everybody. Today, my team's going to be talking to you about utilizing mobile LIDAR for highway design projects. My name is Mike Miller. I'm the Traffic Data Manager here in the central office in the Bureau of Programming. And I believe my contact information, along with everybody else, is shown on page 15 of your handouts. So while I've got that information up, how many people here would say that they know a lot about mobile LIDAR, extensive knowledge of mobile LIDAR? Anyone? Got one. Good. So then is it safe to assume everybody else has limited knowledge of mobile LIDAR? Me too. Me too. That's the way I was before we started this project. I knew what it was, I didn't know a lot about it. Since we started, I've learned a great deal, and our hope is that at the end of our presentation that you guys will know a lot more about than you did when you came in here, and then we can show you the pros and cons of mobile LIDAR and how we feel it can benefit the department. Anybody heard the term point cloud? More hands. So you guys know more about mobile LIDAR than you let on. Okay. So point cloud. The kind of technical definition of a point cloud is a geospatially accurate group of points, all containing X, Y, and Z coordinate. Each of these points also contain associated metadata, such as RGB values and intensity return values. These values allow you to delineate features within the point cloud. So basically, a point cloud is a working 3D model that you're looking at that can be used for numerous things, including asset inventory, design, as-built, etc. So when I first heard that definition, I'm like, okay, what's all that mean? Right over my head. So let's look at it this way. You guys might want to get out of the middle here because the interstate's getting ready to come right to the middle of the hallway here. So, woo! Mobile LIDAR vehicle just went through here on this interstate. Okay? We got people on the right, we got people on the left. And all those points that you see up there on the screen, every one of those little bitty tiny red dots has information associated with it. Every one of us got an X, Y, and Z coordinate. Every one of them has associated metadata that goes with it. Millions of points. So if we had this highway running right through the middle of this hallway here, or I guess there is a hallway, every one of you would be covered with these red dots. The ceiling would be red dots. The walls, above the table, below the table. Okay, well maybe not below the table. Everywhere, the floor. All right, now. Brandon, I got him at the end, he's a big strong guy. I'm going to have him take that wall, and he's going to push that wall until this room is a mile long. Go ahead. We'll wait. So imagine this room, as wide as it is, a mile long. Points, millions of points, on the wall, on the ceiling, on the floor. And you know how long it takes to get that data? 1 minute. Roughly a minute, 60 seconds. Because the mobile LIDAR vehicles basically run into speed traffic. All right, they can run 55, 60 miles an hour and collect all of this data. Think about the amount of information you can do with this. I remember me being an old surveyor, most of my young colleagues here, back in the 80s, yes, 80s. I was out on the survey crew, and we'd be working, doing this topographic survey in town. We'd set a PK out this intersection, PK out that intersection. We'd run our chain down the middle of the road, paint our stations every 100 feet, and then we'd go out there with a cloth tape, slap our 90s, coordinates, and locate all of our topo. Whole way of doing it. Slow, tedious. So that when I saw this new technology, it's nothing short of remarkable in my mind. when you look at this, and here's another thing to keep in mind. You guys familiar with drones? Right? You know what drones are? They fly over, they got the cameras. This is nothing more than a snapshot of a point cloud. Okay, a point cloud is a 3D model. It rotates. You can take, and in the computer, you can look at any view you want at any angle. And that's all this is just a clip, snapshot of that 3D model. But the clarity is really excellent. You can see the barrels, the sand barrels in front of the pier, the pier path. You can see the beams, okay, the vegetation, the striping. This is what really gets me too. You look at this picture, again, you can see the striping, okay? This thing, it's even picking up shadows on the paper of the guy walking along the paper. And then one final picture here as well. The vehicle, the man walking, again, shadow. You've got guardrail, you've got in between the stripes, you can see the raised pavement markers. You got riprap, you got abutments, you got wing walls, you can see it all. So let's break it down. How are we doing things right now? Well, for example, in our current CRS contract, they incorporated mobile LIDAR with our normal CRS data collection methods. So in 2017 and 2018, we collected mobile LIDAR. 2018, 2019, the 4-year contract, we will not. In addition to that, a lot of our local district survey crews collect their own stationary LIDAR for projects within their own district. Consultant project, this project will look at a past project in one of our districts where a consultant utilized mobile LIDAR. And it started off kind of on shaky ground. But by the time everything got sorted out, they ended up with some really good data, very accurate, reliable data. Intangible benefits to consider when you're looking at mobile LIDAR. The things that maybe don't come immediately to mind. You know, one of the most important one of those would be safety. Safety for surveyors in the field, both IDOT staff and consultants. Data storage considerations. Sometimes this gets overlooked. When you look at those pictures, when you think about that 3D model, those are huge, huge files, big data. So a lot of thought has to go into the hardware and software needed to store and run that data. And then we'll look at moving forward with mobile LIDAR. You know, break down the pros and cons, how we feel that IDOT would benefit from increased use, both IDOT and consultant staff. So here's some definitions. This isn't all the ones you'll hear today, but it's you know, probably some of the major ones you'll hear. These are shown on page 1 of your handouts. So in case anybody didn't know what LIDAR represents, it's light detection and ranging. CRS, condition rating survey, that's basically also within our Bureau programming, where they go out and determine the condition of our existing roadways. DMI, distance measuring instrument, is an instrument that's on the mobile LIDAR unit of the CRS vehicle, which determines the position of the vehicle or distance along the roadway. Vertical clearance measurement, that's checking your distance for your overhead structures where they cross the pavement. And then your GNS and GPS are your satellite system used to get your coordinate geometry. So like I said, mobile LIDAR has seen limited use in the past, but due to people learning more about it and realizing the advantages it offers, the use of it has been increasing, and I would suspect that it's going to continue to do that. So like I mentioned, we have a 4-year contract with Manley Communications out of Madison, Wisconsin. And like I said, the first 2 years of that contract, We were collecting mobile LIDAR for asset allocation, 17 and 18, and in 19 and 20, we will not be collecting the mobile LIDAR. We'll see what we do in the next contract after that. Talking about the CRS data collection, we basically collect CRS half the state each year. We collect all state jurisdiction routes and all NHS routes, both local and state jurisdiction. So in the even-numbered years, we collect Cook County in District 1, along with Districts 4, 5, 8, and 9. In the odd-numbered years, we collect the other 5 taller counties in District 1, along with Districts 2, 3, 6, and 7. And a map delineating that coverage is also shown in your handouts on page 2. We collect CRS data for interstates every year. And anytime we're doing CRS, we basically avoid unpaved roads. And on average, we collect 13,000 to 16,000 centerline miles of CRS data every year. So current estimates for CRS photo log and mobile LIDAR data collection, including vertical clearance measurements and point cloud delivery, is roughly $1.3 million. CRS collection alone is about $750,000, with another $500,000 for point cloud creation. But like I said, LIDAR is not used every year in CRS contracts, so obviously those years would be less expensive. Now, the LIDAR data that's being collected now is still very valuable, even though it's mapping grade. You know, it's being used to develop roadside inventory, such as guardrail, signs, pavement markers, what have you. And that could be used for building and maintaining an accurate asset management database. But like I said, unfortunately, it is not survey grade, and therefore can't be used for design survey work. So if we upgraded that LIDAR data to survey grade data, it would eliminate the need of complete resurveys of pavements that we've already surveyed. So obviously future projects that require design work are going to need field survey work done. And this is accomplished either through our own IDOT district survey staff or through the professional transportation bulletins where we award the work to consultants. So now, based on discussions I've had with a couple of the chief surveyors in the districts, with the exception of District 1, most of the districts do a lot of their own design survey work themselves with their own crews. However, there's still a substantial amount of data of work that is done by consultants through the PTVs. So how much we spend? So without looking at your little handouts, anybody want to fathom a guess how much a year we're spending on projects that include design survey work? Guesses?
$2 million.
How much?
$2 million.
Good guess. $2 million. It's about $3.5 million a year. I went back and researched the last 5 years of professional transportation bulletins. Found 44 projects, which were mainly phase 2 projects, that included some design survey work. Those also came with estimated contract amounts. Now obviously, that's a conservative amount because the total of those projects is going to include things like, plan prep, administration costs, design time. It's not all design survey work, but I wasn't given the breakdown on how the work was invoiced to be able to give you a more definite number of what percentage of those contracts was design survey work. But the thought process is, for instance, if we have our own mobile LIDAR unit, that project's eliminated completely. So $3.5 million a year. The breakdown of that is shown on page 3 of your handout, which shows all the PTV numbers and item numbers on the PTV and the estimated project cost, where I came up with this figure. combine the cost of CRS data collection with mobile LIDAR and the amount of work awarded to consultants through the PTVs, we're spending close to $5 million a year to get field survey data currently. And again, like I said, switching from mapping grade to survey grade would better utilize the department's resources in several ways. It would reduce the number of consultant contracts that we award through the PTV by utilizing our own mobile LIDAR unit instead of letting it go out. It would save valuable internal resources of time and expense with our own survey crews, which in some cases use conventional field surveying methods, where mobile LIDAR would be a much more efficient way to collect the data. Probably the most important point is it will improve the safety greatly of not only our survey crews, but the consultant survey crews as well. So I've thrown a lot at you already. They're going to throw a whole lot more. A lot of questions to be answered. Big decisions. So how do safety concerns affect our decision to utilize mobile LIDAR? That's a lot of data, especially you get a lot of projects. How are we going to handle all that data? What's the real difference between mapping grade and survey grade? Is it a big deal? Is it necessary? So should we upgrade the mobile LIDAR from mapping grade to survey grade on the CRS work itself? Should IDOT purchase their own mobile LIDAR unit for in-house survey work and be used in any districts? Or if we really want to spend some money, perhaps incorporate both options. These questions are going to be addressed by the rest of my team during our presentation. With that, our next speaker is Pete Burles.
Good morning, everybody. My name is Pete Burles. I'm the Chief of Surveys for IDOT District 3. Just want to start out by saying I'm very thankful this morning for stretchable waistlines. I've had to wear a suit in quite some time. I came to IDOT in 2010 from a smaller, from managing a survey division of a smaller office. Probably the highlight of my career was working on the renovation of Chicago Bears Stadium years ago. Kind of an interesting note on that job is when we were surveying that job, we found an old lab. I don't know how many of you know, but under Soldier Field is actually one of the sites where they developed the nuclear bomb. Just want to say to all the higher ups in this room, you're all under arrest. The survey police are coming to get you. This is actually a state statute. Just want to point out from this that topographic surveys that are going to be used for design purposes need to be done under the direct supervision of a surveyor. Engineers can do it, but it is specifically for the project that they're going to be working on. Basically, just kind of pointing this out as we explore measuring technologies, please involve your district surveyors. What I'm going to be discussing today is the mobile LIDAR project that we did in District 3, and also going to be going into a little bit about TopoDot software. In our research, we found that TopoDot software is the leading software for dealing with point clouds. It's used by over 30 DOTs, of which we are not currently one of them. So let's start out with the project. This survey that we did the mobile LIDAR, use the mobile LIDAR unit, is a portion of I-57 near the Chabans area in our district. Let me start out by kind of getting into the term survey grade. What is survey grade LIDAR data? Basically what I want to point out on this is that the 4/10 in the northing, that's a little less than half foot, 4/10 in the easting, nothing to worry about. We can easily achieve that with either mapping grade or survey grade LIDAR. The big thing that determines survey grade LIDAR is the 400ths in elevation and 800ths relative to a datum, or sea level basically. So in order for it to be considered map or survey grade, we have to be within a ½ inch in measuring between points of accuracy, and we're allowed to be within 800ths of a datum. After we set our control on a job, typically we should get that down to 100th or 2. So the big term to remember is about 600ths as we get into survey grade. So our job begins. We had consultant A, and they were going to do the conventional survey work on this job, and they contracted out to consultant B, and they were going to do the mobile LIDAR acquisition. Before they started the job, I asked them to send us the piece of equipment that they would be using for this job. And what I found out is what they were using in Trimble has a survey grade unit, but that was not the unit that they were going to be using. They were going to be using a mapping grade unit. And the accuracies from the spec sheet spec'd out to be 600ths to 1600ths. Well, that will not give us the data that we need for survey grade, so we went back to, well, I'll get into that in the next slide. So basically they weren't using a piece of equipment that would have given us the data that we need. So what we did is told consultant B to go out there and do some more research and try and obtain a unit that would give us survey grade accuracies. And basically they sent back and said, it can't be done. We don't believe achieving 400ths in elevation accuracy is possible at the 95% confidence level, and using mobile LIDAR is not practicable. If you guys want to do this, you have to use terrestrial LIDAR. So we had a talk with consultant A and said, can you add another consultant to this contract? Somebody who feels that it's possible and has the proper equipment to perform this job. So they did. They went out and through quite a bit of work having to add another consultant onto the contract. They brought on consultant C, and they were going to use the Leica Pegasus system. And when examining the spec sheet for that, we found that it absolutely would seem to spec out to meet the requirements for survey grade mobile LIDAR accuracy. The other thing to kind of point out on this is if you look at the unit itself, it's something that, as we look for funding in this, that you might look to emergency management, something that could easily be mounted on top of a Hummer in case of a natural disaster or, God forbid, a terrorist attack. And combine this with a drone and the point cloud data that you get on the ground, you'd be able to get a pretty quick idea of what's going on the ground. Okay, so the job begins. IDOT District 3, we were going to provide them with the overall horizontal and vertical control. Consultant A was going to complete the conventional survey work going from edge of pavement out to the right-of-way and the island stuff in between. Consultant B was going to complete the level run and establish northern, easting, and elevation on the chevrons, which are used to control the mobile LIDAR and get us those survey grade accuracies. And then consultant C was going to do the mobile LIDAR acquisition. This is what's called a chevron. This is an example of what's used to control the mobile LIDAR to get it to survey grade. These paint marks are put out on the shoulders, and as you'll notice at the tip, there's a PK nail. And what they'll do is they'll use, a survey crew will GPS that PK nail, and then they'll do a conventional level run through those nails to establish the elevation. So the job begins. I think the job's done, and I get an email in the morning, and it's basically, Houston, we have a problem. Consultant A is on their way to submit the work that was done, and basically, in the email they told me that the numbers don't match very well between the mobile LIDAR data and the conventional survey shots that they took on centerline to compare the two. So I knew right away once this information came in that I was going to have to start to examine the data. So what I did right off the bat is I looked for an area on this project where the elevation difference between the conventional survey shot and what they were calling the LIDAR data was going to be large enough to stand out as far as when we went to check it and measure the difference. So I found an area where the difference was 12 hundredths of air. Again, keeping in mind that the air shouldn't be more than 6 hundredths. So once I got the data from all the consultants, I took a look at the point cloud and the conventional survey shot, which here is in blue, and that little white dot, which is, or the white dot is a conventional survey shot, I'm sorry. The blue dot here is a shot that consultant C extracted from the point cloud. So what they were doing was comparing an extrapolated point versus the conventional survey shot point with the actual point cloud point. And I noticed right away that that difference between those 2 points was actually a little over 5.5 feet. For the engineers in the room, 5.5 feet at 2% is about 11 hundredths. So that could be the error measurement right off the bat. So what I did is I compared that conventional survey shot with the point cloud itself, and I found that that knocked the error down to 7 hundredths, still on the high end, 0.0675, so 7 hundredths, and I wanted to dig a little bit deeper because it seemed like the data should be better. And in digging a little bit deeper, I found a letter that was part of the submittal package that I don't think was intended to reach us. And basically, it said that consultant B kind of started on a point on the south end and looped itself around and closed back on that south end, ignoring our intermediate control. And when they did that, they distributed their error, and after they distributed their error, they were within 4 hundredths for most of the points, but a few were in the 5 to 7 hundredth range. Well, right off the bat, that's a red flag, because this data, after we provide them with the control, they should be within 100th or 2 when they're running their level runs. In order to establish the site control, we ran between 2 NGS monuments. We ran 9 miles, and we had less than 100th of air of closure per mile, basically, after we prorated that out. We set benchmarks every 1,000 to 1,500 feet, which we expected the consultants to close into for each segment of the project. And with that being said, the elevation error should be 0 to 2 hundredths, not 3 to 7 hundredths, as that's the control that's controlling the point cloud. So I looked into consultant A's level runs. They were doing the conventional survey work and found that they kind of did things the way we desired for them to do, and they did close within 100th or 2 typically on their, well, on the bench runs they closed within 100. Again, consultant B, they held the point at the south end, ran a whole level loop, and redistributed air. So in essence, they kind of created their own datum for this job, which was different than our elevation control. And so basically, I went back to them and said, look, your elevation error should be within 100th or 2, not 300ths to 700ths. You guys need to use our control. They basically said, we did use your control, but we'll go ahead and redo it. So I guess that's lawyer talk. So again, went back to them and said, look, you've got to hold our control. And then once you guys redo the data, if you could show me the data before we ship it off to consultant C for them to reprocess. And when I got the data back from them, I found out that 76 out of 167 control marks or chevrons were in that 3 to 500th range. So 46% of the points were gonna need to be adjusted in the point cloud. As a result of that, I knew that we'd be getting better data once this readjustment happened. So I shipped it off, or the data was shipped off to consultant C for them to readjust the point cloud. The point cloud came back, and I did a check now of the conventional survey shot in that same location, and we closed within 0.0045 or less than 100th. For the type of work we do, you can kind of consider that an immeasurable difference. I took it a step further and said I'm going to compare all the conventional survey check shots that consultant A did, and I'm going to look for anything that's 700ths or greater, and do that comparison. Basically, that 700ths, once again, 400ths for that absolute measurement, and 200ths for that datum error. And when I did that, only 4 of the 272 shots in this new point cloud had a difference of 700ths or greater. So knowing that consultant A didn't use a robotic total station, I sent our survey crew back out there with a robotic total station to check those 4 locations. And once they did, the data came back, and I did provide them with elevations so they didn't know there was no bias. And once they came back, 100% of those shots all fell within the acceptable range. Next, I'm going to get into software called TopoDot. One thing I want you to realize, let me back up a second here. We were able to successfully complete this job with the software that we do have. TopoDot does have some unique analysis tools and can more effectively handle and deal with this large point cloud data. Another thing that I want you guys to realize once I start this video is that this operates within Bentley Suite, so it's just additional tools that currently work within our Bentley software. There's no sound, so I'll be able to hear anybody who's snoring in the room. This first tool analyzes a pavement condition as a result of the mobile LIDAR data that's been collected. Kind of points out any potholes, and then it'll complete some reports and give a road rating as a result of the information that has been acquired through point cloud. Establish a pavement condition. This next one basically looks for wall monitoring or movement in walls, both in the horizontal and vertical, or bulging of the walls. Basically, over a period of time, you do multiple observations, and then it'll compare that point cloud data and note the differences for you and complete a nice report for you. Another thing about TopoDot, it seems like unlike other software vendors, they're eager to create new tools for departments of transportation, and they're very receptive to input and creating new tools for us. So again, this is just showing the differences that it detected between measurements of the data over a period of time. This next one I think would be kind of nice for grid structures. Basically, you define a plane, and then it takes and analyzes that point cloud relative to that plane. So I think it'd be a good tool for kind of looking at the plumbness of the wall. Once again, here it's pointing out those differences, kind of highlighting it in color also. Preparing a nice report for you, color coded so you can see those areas where it deviates substantially. This next one is a pretty neat tool. It quickly establishes from the point cloud the highest and lowest areas of separation. And then it zooms into those areas to show you what it's measuring to in that point cloud. So you know exactly what you're getting. And from what I'm told, you can actually extend out a plane to account for the sag situation with the truck going underneath. In our district, we have done some terrestrial LIDAR scans to establish the elevations of wires relative to the pavement. This is a quick analysis tool for that. This, I think, is a really cool tool. It allows you to do the grade analysis of the pavement. So for resurfacing projects, we'd be able to point out those areas where the grade really needs to be paid attention to when it's resurfaced. This tool is a speed advisory tool, and what it does is it analyzes the point cloud and then lets you know which areas don't meet the requirements of the minimum speed for that area, and it highlights those areas as a result of the analyzing the elevations of the point cloud and radii. And this final one looks at vehicle collision, or basically in this example will show you whether or not that radius is large enough for a vehicle to make that turn. It's kind of pretty neat. It highlights the areas when it starts to go off the road. So with that kind of being said, I'll give you a kind of a brief highlight of pricing. This can all be found on Topodot's website if you guys want to look into this some more. Basically, to get in, what this is it's a use per user per day fee is how they bill. And there's an initial fee on the low end of $81.50, on the high end of $18,900, depending on how many days of usage you want to purchase. And then after that number of days expires, they bill you an additional fee for that usage. So basically, that initial fee is the fee to get in, and then you'll be billed accordingly per day of usage per user. And that's the end of my portion of the presentation.
I'm Jeff Wood with the Central Bureau of Bridges and Structures. Today I'll be talking about intangible benefits to consider when utilizing mobile LIDAR. Intangible benefits are unquantifiable benefits without any added cost or data from previous history. Some of the more important benefits include increased safety, higher data collection speed, higher accuracy data, and an up-to-date, data-rich geospatial point cloud for use in a lot of other business practices. On page 8 in our handout, show a list from the Washington DOT and the UC Davis research of business areas that they found that could benefit the most from mobile LIDAR that they didn't originally think of. An internal poll was conducted with all of the district chief of surveys, and they were asked to rank in order of importance why they wanted mobile LIDAR. The intangible safety benefit was the top of every list. It removes the surveyors and workers from the risk of live traffic on a daily basis. It eliminates the lane closures, which is a public safety benefit also. With no lane closures, traffic continues to flow. There's no static for close calls. We've all had them. No statistic for close calls. We've all had them, and they are terrifying. We also spoke with Caltrans on a conference call through this process. They own and operate 2 mobile LIDAR systems. And one of the quotes that stuck out with all of us in the 2-hour conference call we had with them was, "We made this purchase for safety and safety alone, to get the workers off the roadway." This is just some numbers, statistics from 2017 and 2016 in Illinois, motor vehicle crashes occurring in work zones. 2017, the data is a little bit lower because the final numbers haven't been tallied. They were a lot more than I was expecting. 4,423 total work zone crashes in 2017. 24 were fatal crashes with 30 fatalities and 822 injuries. Most of all, there was 2 worker fatalities in that situation. In 2016, there was 6,744 total work zone crashes. 37 were fatal, with 44 fatalities and 1,273 injuries. Luckily, that year there was only 1 worker fatality, which is 1 too many. Currently, IDOT utilizes conventional survey methods for retrieving roadway data for design projects. Most of the safety procedures utilized during those surveys often include advanced warning signs. That's the most common. Just one set of signs to allow the motorist to know there's people on the roadway up ahead. utilized for the higher ADT situations, but also causes a hindrance to the traveling public. Flaggers and cones can be used on two-way traffic situations. And most of all, they use lookouts and spotters, basically when they have the advanced warning signs if somebody can't have their head looking towards traffic. Every year IDOT survey crews work to locate congested interstate highway pavement. This video is a current survey of Interstate 57 in Franklin County, just to kind of give you an idea. The time it takes to locate one centerline measurement, a mobile LIDAR unit could have approximately surveyed 3 miles of pavement. In this instance, he was just waiting for a break in traffic to run out and get one measurement in the highway. With all of these safety procedures in place, IDOT workers are still at risk and consultants are still at risk anytime they are on or near the pavement, and everybody needs to be alert. Most require additional equipment and staff from other bureaus often require drivers to be alert and focused. This is all at a time when distracted driving it is at or near an all-time high with the new technology of vehicles. It's amazing the number of people that drive by with their head looking at their hands and don't even know you're standing there. With the utilization of mobile LIDAR system, it reduces the worker exposure to traffic and environmental hazards. IDOT surveyors will spend minimum time on the pavement or near the pavement during roadway surveys. They can set their control locations at a safe spot. The chevrons, as Pete pointed out, can be done in an area where traffic is a little bit less. Most data can be collected at highway speeds from the safety of the vehicle. If we are doing data scans in high traffic count locations, there's many options available. Nighttime collection is a big one if photography is not required in that contract. You can utilize off-peak collection time when the higher traffic times are rush hour is not an option. You can also utilize the chase vehicle or TMA to prevent traffic tailgating the LIDAR vehicle to interrupt the point cloud data in certain situations. Mobile LIDAR also serves as a springboard to a lot of other new technologies and safer business practices. Yesterday, Group 1 had a presentation on maintenance autonomy for operations. Many of their autonomy vehicles can utilize this mobile LIDAR for the safer snow plowing and the use of driverless TMAs. Also for project implementation with their as-built plans, their construction inspection and documentation, as well as monitoring and analysis of different projects. And up next is Deborah Taylor.
Hello, my name is Deborah Taylor. I'm a senior .NET developer in the Bureau of Information Processing. And I'm going to talk to you about the data storage considerations with using LIDAR. As in this cartoon, his doctor says that his hair loss is due to worrying about his data loss. Some of the data storage considerations we need to think about is a data management plan, data formats. We'll look at some of the different ones. Data integrity and how to maintain that, your desktop computer needs and any network access needs, and your data backups and archives. How long do you need to keep them and when do you need them? With your data management, different formats we'll look at is how you're going to store the data within your backups. Your integrity is maintaining the assurance of the accuracy and consistency of the data. With the workstations, we'll look at the network needs to process and analyze the data and also just to use the data. The backups and archives, we'll look at when to create them and how long. In your data management plan, you need to determine the coverage that is needed, figure out how you're going to acquire the data, the georeferencing of the data, and how you're going to do that, the processing, and the packaging and delivery. With the coverage needed, you need to look at ways that you can use the data within other bureaus or other state agencies, so that when you go down the highway and you're collecting the LIDAR data, you're only collecting it once and not having to go to the same roadway collecting that same data again. Acquiring the data, we're talking about the actual collection of the raw data. Going down the highway and collecting that data, that's what we mean by acquiring the data. With the georeferencing, you're merging the intrinsic and extrinsic data to produce a point cloud that is tied to the coordinate system. So you tie it to the GPS system and know exactly where that sign or roadway is at. When you're processing and analyzing the data, you're using software such as TopoDoc that Pete showed to manage the data, access the quality, and extract the information necessary for design, engineering, and construction operations. When you're packaging and delivering the data, you want to complete the changes to the data and package it up so that you can give it to the user to be used for design projects. You may want to tile the data, and what that is cut it down into smaller chunks to be able to transport it, and that way it's easily accessed by the user. A few of the data formats we're going to look at is the LAS format, the LAZ format, the E57 format, and the proprietary format. This is not all of them. There are many different formats out there that you can store this data in. All the formats will combine the GPS, IMU, and the laser point data to produce an X, Y, and Z point cloud. With the LAS data format, it is the industry standard. Most widely used, can contain between 20 and 34 bytes per point. And the points may be identified by type and classes, and up to 256 different classes. What the classes are is you're going to say this is a sign, or a roadway, or a guardrail. And it can support waveform data within the format. The only con to it is you can't store the images within the format. So the images would have to be stored outside. Now with the LAZ format, it is a compressed version of the LAS. It will be 10 to 20% smaller than the LAS files, and you can use software called LAS zip to compress it and uncompress it. It is good for backup and archives due to the smaller storage. But you cannot compress any LAS files that contain waveform data. It doesn't work. With the E57 format, it supports image data, and it has internal checksums to check for corruption. But it's not easily workable. You have to have a special reader and writer in order to use that format. And it's not used by numerous vendors. There is also proprietary formats which are created by the vendors themselves. That is good because it's supported by one vendor for support and maintenance, but it's also bad on the same reason. What if they decide they don't want to enhance it anymore? Or they don't want to bring it up to more features? The data integrity, some of the things you need to think about is checking the data for changes. Possibly using RAD, redundant arrays of independent disk, and taking snapshots of the data. When you're checking the data for changes, all you really have to do is possibly bring it up within a year or 2 years and see if you can still read it. If you're using the RAD, the arrays can reduce corruption and detect problems for you. It allows for greater performance, reliability, and large volumes of data to be stored. It splits the data onto multiple disks and uses error corrections that are built into it. Taking snapshots is just what it says, taking a snapshot throughout the day while you're processing the data. That way, if you have to go back, you can go back to that point in time and not have to go back to the beginning of the day or the beginning of the week and lose everything you've done. And looking at the desktop computer specifications, I did some research online, and we also talked to California, who's been using LIDAR for a while, and they recommend a 64-bit operating system. Good graphic capabilities. Monitors with high resolution, using solid-state drives, and RAM, as much RAM as possible. The solid-state drive, they recommend at least a 500-gigabyte drive. The solid-state drives, or SSDs, have access speeds that are faster, and they're not as easily corruptible due to the lack of magnetic medium. With the RAM, it was recommended that you only have 8 gigabytes, but to me, that's not a lot when you're talking about processing speeds that you need. In California, they use an HP Z480 machine with a 128 gigabyte of RAM for processing. They said they found this to be the best machine. When you're talking about the local area network, what you need, you can either have a local network, a local area network or LAN, or a wide area network, which is just WAN. With the local, you're storing the files on one workstation. For both processing and analyzing, this is good because the speed will be a lot faster. But the cons to that is if the workstation is powered off, you can't get to it, and there's no centralized control. With the local area network, the files are stored on a local file server. It's easier to administer and can hold a lot more data, but you really need a high-speed connection in order to get to it. With the WAN, the files are stored locally, or not stored locally, they're stored like in cloud storage. This is good for backups and archives, but will be very slow when you're trying to process and analyze the data. Unless you can get a dedicated network line to that cloud. When you're talking about the data backups and archives, you can talk about when to back them up, the data retention schedule, disaster recovery plan, and the sunset plan. When you're talking about when to back them up, you also need to know where. You can back them up in the cloud or in the file system, as I said. But you may want to do a combination of both. Backups is how often do you want to back it up. If it's the raw data that you just collected when you went down the road, it's not going to change. So you only need to back that up once. If it's the dynamic data that you're working with every day and you're processing to get ready to hand off to the users, you may want to back that up multiple times because it's going to change frequently. The data retention schedule, how long do you want to keep that data? Does it need to be kept with the entire project for the life of the project for 7 to 10 years? Or only a shorter period of time? That needs to be outlined. Your disaster recovery plan. So if a disaster happens at IDOT, what are you going to do? Where's your data going to be? So you need to store your data in an off-site area so that you have that data when you need it. A sunset plan is allowing for changes within the system. So if the software changes or you want to change to a new software yourself, being able to convert that data and thinking about how you're going to change that data so that it can be used later. This is a data storage example. It's on page 9 of your handout. It's 8 miles of interstate with 2 to 3 lanes in each direction, and it was taken in Oregon. It shows the main line and the ramps and frontage roads. It shows for that 8 miles, they had to travel 65 miles in order to get all the LIDAR data. The raw files themselves took 109 gigabytes of storage. When they processed that data, it took 204 gigabytes, almost double the raw. Then when they packaged it up and got it ready to deliver, it took 168 gigabytes. So for this 8-mile project, it took 481 gigabytes of data storage to get that ready to go. And that doesn't include all the extra backups you might have wanted to do. So we have to think about the data when we want to think about using LIDAR data in the future. So that we have plenty of storage and we don't have to stop when we get halfway down through a project. this over to Paul for the rest of our presentation.
All right, my name is Paul Klotz, and I'm the Chief of Surveys for District 9's Bureau of Program Development. Today I'm going to talk about moving forward with mobile LIDAR. We want to know, what does the future look like at IDEM? So first I asked the question, why do we want mobile LIDAR data? Jeff revealed that internally our #1 priority was safety. Following that, we saw productivity and cost savings. So with productivity, we see an increased speed in data collection. One data collection can be mined over and over by multiple people doing multiple things, and the data can serve as a base map for the future. With cost savings, we see less time spent surveying. It can eliminate return trips to the field, and everyone can use the same data, eliminating the need for potential multiple data acquisitions. So let's talk about the current mobile LIDAR collection at IDOT. As Mike mentioned, we have the CRS collection through Mantley Communications, but we also have 2 central office consultants that can supply aerial mapping and mobile LIDAR services. All right, so what makes LIDAR survey grade? We have a laser scanner sensor, GPS antenna, an inertial measurement unit or an IMU, and we have control. So a laser scanner sensor contains a rotating mirror, and the speed at which that rotates can allow us to collect data at speeds of 1 million points per second. And with a survey grade instrument, that mirror speed is about 250 times per second. Compare that to mapping grade, which is only 20 times per second. We also see that we have range accuracy of our lasers of between 1 and 5 millimeters for survey grade, comparing that to only 20 millimeter accuracies for mapping grade. And to get the absolute accuracy of that data, you have to double those numbers, meaning that survey grade could be as accurate as 2 millimeters compared to 40 millimeters for mapping grade. So that's nearly 20 times the amount of error in mapping grade when you compare it to survey grade. We also have the GPS antenna. So the GPS antenna on a survey grade unit is already configured to receive up to 4 global navigation satellite systems. Many of those satellites have yet to be launched, so as time progresses, we'll see better and more geometry, whereas a mapping grade GPS antenna is typically only configured to receive one of those global navigation satellite systems. So what is an inertial measurement unit? It's comprised of gyroscopes and accelerometers that can measure linear and angular motion. It's continually correcting for the position and orientation of the sensor to eliminate errors, and it's the component that can generate positional data in a GPS-denied environment. For example, if we're traveling underneath an overpass and we don't have satellite information, the unit will then rely on the IMU to create that positional information. So a survey grade unit utilizes a tactical military grade IMU compared to mapping grade, which uses a cheaper consumer model. And then Pete talked about it, we have control points. We still do control on the ground. Those points are visualized in the scan, so we process the data through those control points to further eliminate errors, and we can match a specific data that we're trying to achieve. So where does technology advance from here, and how quickly? One of our concerns was technology becoming obsolete in the near future because of rapid advancements. So we asked different industry professionals about this, and here's some of the answers we got. At the moment, mobile mapping technologies are at a peak plateau. Another response was, we are at a reasonable technology standpoint. So we asked them to supply us with information to support these statements. In regards to the technology advancement plateau, they stated that mirror rotation has currently been maxed out at 250 times per second, and in fact, most data collections are occurring at a slower rate of speed because at 250 times per second, the point cloud starts to introduce a lot of noise or extraneous data that really just isn't there. They also mentioned that the current laser wavelength has been the industry standard for the past 8 years, and it's giving us the best return for hard surfaces. IMUs have currently reached military restrictions, so they don't see any advancements in the near future. As I talked about, GPS antennas are already configured to receive those future satellite launches. And at this point, smaller units are sacrificing in accuracy. So with a mapping grade unit, we're seeing very small and compact units, and they're just not able to obtain those high accuracy standards that we're looking for. And in regards to technology upgrades, they assured us that current survey-grade mobile LiDAR units already contain the ports for future technology upgrades such as better cameras or technology add-ons such as ground-penetrating radar. So you can simply just connect these future technologies to existing units. So it's not like the unit's going to be obsolete if future advancements occur. They also mentioned that the computer interface unit, which is a separate component that logs the data and communicates to the unit itself, can be replaced at a relatively low cost in comparison to the whole unit. So what's the lifespan of a mobile LiDAR unit? After talking to multiple vendors and industry users, they stated that 10 to 12 years is the expected minimum life of the mobile LiDAR unit. So how do we cover the cost of replacement? For example, what if the instrument was to be damaged or destroyed in an accident? Well, we know we have a self-insured option at IDOT, but that really doesn't seem like a very good choice for this high-dollar piece of equipment. So upon further investigation, we found out that CMS also has a master broker on contract that can put out a bid for us for external insurance for expensive pieces of equipment like this. And we estimate that that policy would look something like $10,000 per year to cover a unit for $800,000. We also spoke with Caltrans, and they stated that they cover both of their survey-grade mobile LiDAR units for a price of $8,000 per year, and that gets them $1 million in coverage for each. So in our current state, can we handle a mobile LiDAR unit? We're going to have staffing concerns, training and software needs, and we're going to have IT challenges. So we're going to need drivers and operators for the unit. We're also going to need technicians to process and extract the data, and we're going to need a PLS for quality assurance. We're also going to need to develop a best practices workflow, as well as get training on the acquisition, processing, and extraction of the data. And we're going to need the software to be able to do those types of things. Another thing is the IT challenges, and Deborah talked to you a lot about those issues. So what will it cost to acquire a survey-grade mobile LiDAR system? We received quotes from 3 separate vendors, Leica, Regal, and Trimble, and they all contain different add-ons and components, and approximately what we see is about $700,000 for a purchase price. And in addition to this, you'll see about a $65,000 cost to get it set up on a vehicle. So what about the other costs involved? Well, in 2011, Washington State DOT commissioned the University of California at Davis to perform research into seven different mobile LiDAR acquisition options for the purpose of asset management and inventory. The scenario they used was collecting all of their highway data in 2-year cycles for a period of 6 years. 6 years was used as their conservative estimate for the life of a mobile LiDAR unit. So if you refer to page 10 in your handouts, you'll see table 3.9, the itemized cost for purchasing and operating a survey-grade mobile LiDAR unit. You can see that approximately $1.2 million account for the IT cost. They also estimated $2.3 million in data collection cost. And that included the purchase price of the unit, the vehicle, the maintenance, the training, and the personnel costs to operate. They also estimated a whopping $4.5 million in data extraction. And that cost is basically just comprised of the hours of labor involved to extract the data itself. So they estimated a total of approximately $8 million for this option. So how did that cost compare to other options? You can refer to page 11 in your handouts, and you'll see table 3.11, the cost summary of all 7 options. We're only focused on 4 of those options, and on the left-hand side of the bar graph, you'll see the total price per option, and along the bottom, you'll see the different options listed. So let's look at option 1, which is the first bar. That's contracting map and grade mobile LIDAR services. They estimated a total cost of $7.1 million. Compare that to option 4, which was purchasing and operating a map and grade mobile LIDAR unit internally. The price drops to approximately $5.8 million. So what you can see here is that when you compare apples to apples, internal collection versus contracting the same collection, you can realize about 20% in savings. So now let's look at option 1 and 2. That's contracting map and grade mobile LIDAR with obtaining vertical clearance measurements for our structures. That total price was about $8.1 million. Compare that to option 6, which was purchase and operate a survey-grade mobile LIDAR unit internally. That cost, as we saw from the previous slide, was approximately $8 million. So it's not a lot cheaper than options 1 and 2 combined, but the important takeaway is that you can actually purchase, operate, and collect all of your data in survey grade for cheaper than you can pay a consultant to collect that same information in mapping grade. So is the investment worth the return? Referring to page 12 in your handouts, you'll see table 3.14, the itemized savings for each mobile LIDAR option. So what they first had to determine was how much were they currently paying for conventional or traditional data collection methods for their assets. They then subtracted out the mobile LIDAR options, the cost of those options, and they were left with a potential savings for each option. So looking at option 1 again, which was contracting the mapping grade mobile LIDAR, they could realize a potential $4.2 million in savings. Compare that to option 4 again, which was purchasing and operating the mapping grade system internally. That could realize $5.6 million in potential savings. Options 1 and 2, which was contracting mapping grade mobile LIDAR with acquiring the vertical clearance measurements. Again, $5.6 million in potential savings. And let's compare that to option 6, which was purchasing and operating the survey grade mobile LIDAR system. Potential savings of $6.1 million. Now, if you remember from the previous slide, the last 2 options were pretty comparable in price, but now that we see the potential savings, survey grade mobile LIDAR has the ability to save us more money. Well, why is that? They determined that there were certain asset collections that were dependent upon accurate elevation information, such as those vertical clearance measurements and ADA rates. And survey grade accuracies were able to meet those standards, so they could realize a potential greater savings. Now, what they don't include in their potential savings is that survey grade mobile LIDAR can be used for design surveys as well. They noted that if you used your survey grade mobile LIDAR unit for only 40 miles of design survey each year, that alone would be enough to offset the upfront cost of purchasing a survey grade mobile LIDAR system. And at the time that they did this study, Washington State had spent 5 years collecting assets, and they estimated that they had another 4 years to go just to complete one cycle. And with every one of these mobile LIDAR options, they would be able to complete one cycle in only 2 years' time. So in 2016, Caltrans also commissions UC Davis to perform research into the feasibility of purchasing and operating a survey-grade mobile LIDAR system internally for the purposes of only design survey. This is in addition to one survey-grade mobile LIDAR system that Caltrans already operated. So you can see this in page 13 of your handouts. It's table 8, the comparative summary of the cost per project for various options. And we're only focused on 2 of those options. The size of the project that they utilized was a 10-mile stretch of pavement, 2 lanes, so essentially 20 lane miles. Option 1 was contracting for mobile LIDAR services in survey grade, and the average price that Caltrans was paying was, through consultants, was $13.2 thousand. They compared that to option 3, which was purchase and operate a survey grade mobile LIDAR system. The average cost per project was estimated to be $9,000. The way they estimated their average cost per project internally was if they utilized the mobile LIDAR unit for 6 projects per month for a period of 6 years. 6 years, again, was used as the conservative estimate for the life of the mobile LIDAR unit. So you can see this in page 14 of your handouts. It's figure 4, the average cost per project versus the utilization rate per month. On the left-hand side of this line graph, you can see the average cost per project, and along the bottom you see the average utilization for projects each month. So what this is designed to show us is that with internal operation, the more times you use mobile LIDAR each month, the cheaper the average cost of the project gets. Contrary to that is that when you contract out mobile LIDAR services, the average cost per project remains constant and it does not fluctuate based on the amount of times you utilize that service each month. And that can be shown here by the top line in purple. This horizontal line represents the high contractor estimate that they paid versus this horizontal blue line here, which is the low contractor estimate that they paid statewide. What they don't show us on this chart is the average cost per project that they paid, which we know from the previous slide was $13.2 thousand. So looking at the utilization rate at only 4 projects per month, they determined that they were still well below the average price that they paid to their contractors. Additionally, what they wanted to show was that at 10 uses per month, they would be at or below the cheapest price that they paid statewide. So what I wanted to know was, what do we pay for a similar sized project through our current consultants for a mobile LIDAR project? And that can be shown here by this horizontal black line. That's about $15,000 per project through our current consultants that we have on contract. So you can see that the red line here, which is purchasing and operating a survey-grade mobile LIDAR system, falls well below the average price that we pay currently through our contractors. Additionally, what I wanted to know was, what does that data look like if we project out the use for 12 years, which is what we hope the life of the unit will be? That further drops our red line, making the average cost per project even cheaper. And what that does is it crosses over Caltrans' lowest price that they paid at only 7 uses per month. And you can see that it just makes it even cheaper. So again, what I wanted to know was, what's the price per project at 2 uses per month? That was $13.1 thousand. So that's still below their average contractor price and well below what we're currently paying at IDOT. So the takeaway from this chart is that even at low utilization rates, it's still a cost-effective option to purchase and operate survey-grade mobile LIDAR, even if you're going to use it for design surveys only. So that brings me to our recommendation. We do recommend that we purchase and operate a survey-grade mobile LIDAR system. In regards to the technology plateau and the expected lifespan of 10 to 12 years, we feel like it's the right time to procure this piece of equipment. We also recommend that the unit be stored and operated centrally under the guidance of our surveys, mapping, and modeling unit that we currently have here in central office. We believe that internal operation will give us greater control over data collection methods and the processing of the data. And as Pete demonstrated, when dealing with consultants, you can run into a lot of challenges with these areas. Also, in regards to aerial mapping, mobile LIDAR acquisition can occur during all times of the year, where aerial mapping products typically only occur during 2 small windows, one being in the spring and one in the fall. And with the availability of countywide aerial LIDAR, more districts are beginning to use that information for ground contouring and are seeing a higher need for mobile LIDAR pavement surveys, contrary to photogrammetry products. We do recommend the Leica Pegasus 2 unit. We determined that it had the best range accuracy and IMU of all comparable top-of-the-line instruments. Leica also offers local training and support, and their units are serviced domestically. And contrary to that, Leica and Regal units are serviced in Austria, and that can create downtimes of up to 2.5 months. And we do know that District 3 consultants completed mobile LIDAR projects with the Leica Pegasus unit and were able to achieve those survey-grade accuracies that we're looking for. Some of our tangible benefits that one major tangible benefit that we talked about was that survey-grade mobile LIDAR just has the greatest potential for cost savings simply because it has more uses than mapping grade. And some of the main and tangible benefits that we discussed were increased worker safety, public safety, increased data collection speeds can result in faster product delivery times. Mobile LIDAR products can also be used for every bureau within inside IDOT. And the data can serve as a springboard for future technology. So now let's talk about the CRS mapping grade contract. We're currently under contract for the CRS mapping grade, and we do recommend that for the time being, we continue with that contract. Based on the research that we performed or that we read, it still is a value-added expense to the department. Even with the addition of purchasing and operating a survey-grade mobile LIDAR unit. In the meantime, we recommend that we would develop a best practices workflow with the survey-grade mobile LIDAR unit. We would then need to determine our current workload and the maintenance impact it has if it were to be utilized for design surveys, as-built, and other internal uses. We would then want to make a future determination if it's feasible to use the survey-grade mobile LIDAR unit for future asset collections, whether we should expand and purchase a mapping grade unit, or whether or not we would want to continue with the CRS contract that we currently have. So that completes our presentation. I'll now ask the rest of our group to join me up here. Does anyone have any questions?
Yeah, my question concerns safety and data collection in congested areas, specifically, I think like Chicago area. Wondering how fast does that mobile units go, and how sensitive are they to congestion in vehicles, probably say, and also can it be operated at night?
Yes.
Go ahead.
No, go ahead.
So you're asking, how does the mobile LIDAR unit perform in congested areas, and potentially what times of day can we complete projects? So mobile LIDAR can acquire data at speeds of 55 to 60 mile an hour and still achieve like a very dense point cloud. And data can be collected at nighttime to avoid congested traffic, as long as you don't need additional photographs, which most data contains intensity returns, and you can view that data in a way that you can delineate features without having photographs. Also, you can use trail vehicles like a TMA, as he discussed, and that would prevent tailgating. But in very wide areas of pavement, maybe you're talking about maybe 5 lanes wide, the LIDAR unit could potentially make multiple passes, completing 1 lane of traffic at a time, and then you would just filter out the extra data on either side of that unit. So you would basically not be worried about traffic being in the LIDAR scans, because that could create holes in your data. So you would just drive each lane separately if you were in a situation where there was a lot of traffic passing the LIDAR.
And kind of get a little further, that slide that you saw earlier in the presentation when we showed you slides of point clouds, that's what Paul's talking about, what they look like without the photos, what's called RGB factor added to the points themselves. So that's what the data would look like. And I have done some collection at nighttime with our terrestrial machines that we have, and it looks exactly like that. So you're able to delineate good data. And for the collection we did in our district, all we had was a trailer vehicle follow, and it was during traffic hours. Obviously, District 3 isn't as congested as District 1, but by having that vehicle kind of follow and make sure nobody cuts in between, you're still getting really clean data.
So if you had a single unit, staffing-wise, what kind of staff would you say you would need to support a mobile LIDAR unit?
He's asking what type of staffing concerns we would have if we operated a mobile LIDAR unit internally. So just to operate the unit, you could probably get away with one driver and one operator in the unit. So 2 people to operate the unit in the field. And then depending on your workload with the unit, that would determine how many technicians you would need for data extraction purposes. You would have the option to extract data at the central office level, or you could let the districts handle that with their current survey staff. And you could also make a determination, maybe current management would, if we have underutilized staff, they could possibly be performing some of those duties. So with collecting just design surveys only, that limits the high amount of data that we would get in comparison to collecting assets, which would be collecting LIDAR data from every route in the state, which is, as you saw, basically 50% of your cost in collecting the information. If you're using it for survey grade only, though, you're only extracting data associated with projects that are needed. So it's going to eliminate your staff quite a bit, which is one of the reasons why up front we would only recommend purchasing a unit for the design survey uses only, because asset collections could potentially cause us to have to hire a lot of additional staff.
I'd say too, we probably already have the staff to do this. It's just a matter of training and getting people to catch on to the vision. I think that's the biggest thing of whether this would sit parked in the garage or actually be utilized, would be trying to get the word out and get people to see the vision and the usefulness of that tool. But I think staff-wise, with training, we could accomplish that with probably what we already have, maybe adding an ELS to central office, or just involving district ELSs as part of that collection, which gets a little bit more complicated, but it's definitely doable. Training is a big factor.
I have a question concerning the data collection. So it sounded like with the amount of data that's out there, is that a reason for to go back to servers in the district versus having to run everything to the central office?
Can you repeat the question, please?
Yes. So I know you said there's a lot of data in the computers and things that it took to process that. So currently we're having an issue. You mentioned something, one of you mentioned something about the tile, the network speed, and our issue with that is that we're having, like in District 5, is having to run that through Springfield. Is that something that would be better if the server was back in Springfield to do that?
The question is, with the data, would it be better if the server was in the district itself rather than central office for the speed and the access of the data? My answer is yes. Whether or not that can be done, I don't know. But we do have some servers upstairs for the CRS collection that they're doing, where they're storing the mapping grade data. And if you're doing the processing and analyzing of the extraction of the data, you need that processing speed to be as fast as possible. So the closer the server is to you, the faster it's going to be.
I know for us related to that, for the job that we had done, basically what we've done is we've taken that data, and when we work with it, we're working on our machines locally, and then we dump that data into project-wise as a storage space. So really, you're pulling that data down and working with it locally, even if you have a local server. I may be wrong on that, but I think you'd still want that local to your machine, and then send it back out for storage once you're done.
Given your recommendations are accepted, what kind of timeline do you have to become fully operational? Let's say from the point of procurement forward.
Sounded like from the conversations that we had with sorry. You're asking basically, what's the time frame once we acquire the technology to the implementation of that technology?
Right, and that's assuming you're going to have to do a lot of work in the data area to gear up both at Central as well as all the districts. All that groundwork needs to be done. And what kind of time are you looking at?
Kind of, I think, and maybe unreasonable in saying this, but it sounds like the biggest portion of it would be the training with the equipment itself. We've already kind of ventured down this with the purchase of the terrestrial mobile LIDAR, or terrestrial LIDAR data that we purchased, the equipment that's able to obtain that. So you're really dealing with that same data, so those districts that have embraced it are already pretty far along in dealing with the data itself. So it would really be the training on the equipment, which I think between getting it set up in a vehicle and the training, probably be up and running within a month.
Yeah, I think Leica said that they would spend about a week training you on acquisition, and then they would just let you go out there and start working with the information. And after that, they would come back for additional training after you had time to go out and acquire data to perform a more advanced training as you came up with more questions and issues with how to do the process itself. So it sounds like after about a 1 week training, they feel like users can go out and start acquiring information.
And the initialization process really isn't that complicated of a process. Basically, the vehicle drives and does figure 8 patterns in the parking lot, and then it goes out and just starts collecting the data. So it doesn't seem like it's that complex of a process for the acquisition of data.
So if I understood you correctly, your theory would be the central office would do the maintain the equipment and collect the data, and then the data would be given to the districts to manage, manipulate, and control. Is that correct?
Yeah, so one of the things the question is that if he understands this correctly, our recommendation is that we would have the unit stored and operated essentially under surveys, mapping, and modeling. And one of Caltrain's regrets was that they didn't do this with their units. They actually deployed them out through all the different districts, and so they had to provide training for all the district staff, and they really wish that they would have centralized the use of the unit to make it a lot simpler statewide. And so before they even told us that, we were already thinking that that was the way that we would want to do it in Illinois. And as far as processing the data, it could be a combination of central office or the districts. As Pete mentioned, we already have terrestrial scanners, and once you get that data acquired, it looks no different than a terrestrial scanner data. So we're already training our staff now on how to process and extract the data. So it's not like it's going to be something that we're not equipped or prepared to do.
And also for the job that we're doing right now, the first mobile LIDAR job that I talked about, we did at the district level. It didn't involve central office. We contracted that at the district level. But the current 2 jobs that we're doing through central office, asking for Tony's help to take the mobile LIDAR data, the hard surface data, and combine that with countywide LIDAR that's available for free. And he's hopefully going to create one surface for us that we can utilize for design, basically. So we're getting help from the district in addition to it being us using the data afterwards.
One question I had is, on the mobile LiDAR, one of the issues that you have with it is that it's, again, still line of sight. So if you're talking about on the project stuff, if you have elevation issues at there, are you also then going to be using drones or some other aerial stuff to help with the elevation stuff and adding to the point cloud? Or how are you addressing the elevation issues as far as, again, the mobile is line of sight, so you have issues on some of that?
So the question is, what are we doing? Because there are going to be gaps in the data, it sounds, is what you're saying, with the mobile LIDAR acquisition. How are we going to supplement that data? And we're kind of playing with that at our district level. Basically, there's countywide LIDAR available for our district that's already been done through grant with, through U of I believe. And basically what we're doing is taking that aerial LIDAR that was acquired and splicing in for the hard surfaces, the pavement basically, the mobile LIDAR data. We're also looking a little bit more in these 2 jobs that we're doing currently with central office. We're looking at how accurate is the data once it comes to the side slopes. What we did is we had them go out and mow prior to the mobile LIDAR acquisition. And then we're going to kind of see how good the data is that we get back from the mobile LIDAR for soft surfaces, for the side slopes. But we're supplementing it. For one job, we had conventional survey done outside of the pavement, and we kind of use that. But we're looking at supplementing it with the county-wide data that's available for utilities. And then doing some checks.
Yeah, I'll add to that. So mobile LiDAR is not a replacement for conventional survey in any way. So the main reason we want mobile LiDAR, like we said, was the safety factor. So we want to remove workers from the pavement, right? That's where the live traffic is at, and that's where mobile LiDAR will have the greatest benefit. It's going to be able to pick up those hard surface areas, and then if we have to, as Pete mentioned, we'll go through a conventional survey to fill in the rest of the holes, and those will be in areas that are outside of live traffic. So that's what we're looking for, is that increased safety benefit.
And really what it also gives you in addition to just the safety factor is, you saw the pavement analysis tool in TopoDot software. Really what we're kind of getting now is pretty sparse data, at least in our district when it comes to the interstate. We're not having them go and take shots every foot. You're getting really rich data that you can mine to look at slopes and kind of analyze the condition of the pavement that's currently out there, which you can't really do. This is data that you'll be able to get volumes off of and do volume comparisons, which really we don't have that high quality data right now to do that type of analysis, in my opinion, at least in our district. The shots are so sparse because we don't want people jumping out in live traffic to get those shots.
I have a question about inventory and asset management. I've heard assets a few times, and also how long we can keep this information. I'm curious if this can be tied into documenting inventory and also asset management. I'm thinking specifically of the time a few years ago where we were trying to identify a number of guardrail terminal sections and how many we had. I was just wondering, can we tie all this in and keep that data longer?
So he's asking about the life of the data and can we tie it into asset management and inventory purposes? And the answer is yes. So we already have the CRS collection, which picked up a lot of our routes in the state of Illinois. And that data was processed and delivered to us, so we currently have that. And if you access that data, you can actually go in and extract the features that you're looking for. So if you're looking for guardrail, if it's one of the routes, which it probably sounds like it is, our major routes, you can go in there and measure quantities, you can get location and position on those assets. And so that's kind of what they're talking about, or what we were talking about with asset collections, is you get a data-rich point cloud that visualizes all of your assets along the roadway, and then the extraction cost, which is those hours of labor for man hours, that was the big expense with that type of collection. And that's actually going through all that data, which could be, if it's every route you're talking about. Well, Deborah showed you how much 8 miles of data would be. Talking about the whole state of Illinois, that would be a lot. So you would have a lot more staff to be filtering through that information and then organizing it in a system that we can access to know how many and where our assets are located at. So yes, you can use it for that purpose. That's one of the great benefits of it.
One thing though to keep in mind with that is stuff gets hit. So you don't know what's been hit and might have been replaced with something different. We've noticed in our district, in trying to track all this, really there's a lot of communication that needs to occur to notify us when stuff does get hit. Technology is advancing. They do have handheld scanners now that you can kind of scan, so you might be able to take that section that's been replaced of guardrail. One of the maintenance guys just kind of does a works. And again, this is theory talking, but I do know that they are out there where they might be able to just scan it with a handheld scanner, send us that data, and we can replace it in point cloud itself. So it does become a communication issue to try and make sure that the data we have is up to date and we're being notified of everything that needs to change within the data system is collected.
Yeah, and if I understand correctly, every district has the capability to view the current CRS LIDAR collection, and there should be a dedicated workstation. If you talk to probably your program or planning personnel, they can probably tell you what that information is.
On the equipment side, you mentioned the specs and stuff that California had, and that. So did you guys spec out and say, are the current machines that you're using in surveys and in those areas capable of being able to do that, or are we looking at having to work with CMS and do it to get upgraded specs or whatever to be able to do this in each of the districts?
I think you're asking if the current machines have the specs to complete survey grade accuracy. Well, we don't currently have any mobile LIDAR machines at IDOT. We do have terrestrial scanners which are able to acquire survey grade accuracies.
I think he's talking about the workstations that we have. Are the workstations that we have good enough to do the processing and analyzing of the data that we have? Yes, they'd probably be a little slower. Maybe you can talk to how well it was on your workstation when you processed your project, but I would think that we may want to update some of them, but.
What happened is, at the district level, when they upgraded some machines to power user machines, I've got one of those upgrades, and I'm able to work with that project, no problem on my machine. Well, I won't say no problem, but I'm able to work with the data. We haven't taken it to design. All I'm doing is looking at it from a survey perspective, so I don't know how design's going to be able to handle that once they get there. But as far as the stuff that we have done, which has been mostly ADA ramps and point clouds, they've been able to deal with it. My question would be is, when that initial raw data comes in and all these vector values need to be assigned to millions and millions of points, we don't have a true, we haven't done that yet because that's all been, we don't have this equipment, so that's all been done through consultants. So that would be the question to me is, how well will the machines that we currently have handle that situation? But as far as once we get the data, I believe that as long as the power machines that were upgraded in each district are used, I believe that they can accommodate. We'll have to see on the design end, but everybody's going to want a faster machine for sure, but we can probably run, albeit slowly, with what we have. But I'm going to leave that for the districts to kind of determine. But I found so far that I've been able to work with the data on my machine.